Good morning, Sudhudula Putala. Today we are starting Unit 5, Energetics, Revision plus Paper Class. Up to this to date, we have done all Unit 1, 2, 3, 4, all these revision and also all the tutorial questions and everything without skipping one single question. So I want you guys to go through all these 4 continuously before each term test, get this knowledge back. So otherwise, you are forgetting this. And the second thing is, first 5 units are not that important other than Unit 2. Then when we are moving to Unit 6 questions, then you would use this less and less timing and less priority to these first 5 units, so that now use this opportunity to get the maximum benefit of first 5 units. Okay, so talking to energetics, this unit, this is a very little unit, and this is one of the highly scoring unit, including the kinetics that we are doing right now. In energetics, we are talking about the spontaneity of reactions. What is the spontaneity? Spontaneity means on its occurred, reaction can occur without external influences. So spontaneity defines with this equation, delta G equals delta H minus T delta S. Actually, it's here, you can see. Anyhow, so to decide the spontaneity, we need 2 other parameters. First one is the enthalpy. This is the enthalpy part. Then the second one is entropy. Knowing enthalpy and entropy both together, only knowing both together, we can define spontaneity. To be any reaction spontaneous, this delta G Gibbs free energy value is supposed to be negative. Okay, Gibbs free energy is supposed to be negative. So that to have negative Gibbs free energy, this whole part is supposed to be negative. To make Gibbs free energy negative. To whole part being negative, see, delta G is supposed to be negative, but delta S, this part is supposed to be positive. So this negative multiply this positive become negative. If both these are negative, the possibility of delta G become negative is greater, so that spontaneity is high. So for the system who's having negative enthalpy and positive enthalpy and positive Gibbs free energy are more suitable spontaneity reactions. Okay, so the first part of this unit, so that we are talking about this enthalpy part, delta H part. Then the second part of this unit is that we're going to talk about delta S or the entropy part. Then the last part of this unit is that we make these equations, do these calculations to check whether any given reaction is exothermic or endothermic by calculating Gibbs free energy. Okay, whatever the reaction occurs, that reaction occurs in a system. That reactions occur in a system. So we have to define what is a system. System is the part that we are doing an experiment. So there are, so that system is open to environment. System is open to environment with a boundary. So this limit between system and environment is the boundary. There are 2 different kinds of system we're talking about, open system and closed system. In open system, both energy and matter can be transmitted. Closed system, you can transfer energy but no matter. Then the third type of the system is the isolated system. In isolated system, no energy, no matter can transfer or exchange. Let's start then. Okay, system. environment and boundary. System is the portion of universe which is selected to studying in the system. Environment, rest of the universe other than system is called the environment. Boundary, the marginal line between the system and environment. This can be material or an imaginary thing. Okay, so examples you can just go on and you can just read and understand. Then we are talking about 3 different kinds of systems: open, closed, and isolated. In an open system, both energy and matter can be transmitted. In closed system, only energy can be transmitted, but not the matter. In isolated system, both are not neither energy nor matter can be transmitted. And also, whatever the system consisting with matter, so we can classify properties of matter in 4 different ways: extensive, intensive, macroscopic, and microscopic. Extensive, intensive, macroscopic, and microscopic. What are these? Okay, very easily you can understand extensive and intensive. Get beaker of water. So this much water is here. Now, you are getting exactly same size of 2 different beakers. Beakers doesn't have anything to do. Exactly same glass, same size, same capacity, 2 beakers. Now, I am dividing this water into 2. One part is going to one beaker, the other part is going to other beaker. Whatever the properties are changing, depending on the amount, whatever the properties changing here are called then extensive properties. Okay, as an example that it's obvious, volume is changing, mass is also changing. So whatever the changing stuff going to this extensive properties, properties which are not changing are called intensive properties. As an example, temperature of the water or density of the water, those are not changing. So not changing properties are intensive. If you go like that, it's very easy for you to understand this. Okay. Properties which depend on the amount or size of substance in the system. The value of the extensive property is equal to the sum of extensive properties of smaller part into which the system is divided. Like mass is getting down if you divide, but if you add them together, you are going back to the same total mass. So extensive properties we can add up to get this final. So examples, just go through and read. You have the note with you. You can read all those. Revision means I'm revising and I'm making for you guys to go easily through the note to understand and memorize to go through these questions. Okay, then the intensive properties which are independent of amount or size of the substances. There are a lot of examples. All the examples which are relevant to our syllabus have given here. Okay, so extensive property and intensive properties. So you have this connection. If you get anything, any extensive property per unit something, per unit mole, per unit gram. So dividing extensive property by another extensive property, we can convert into intensive property. That's why enthalpy become extensive, molar enthalpy become intensive, volume become extensive, molar volume become intensive. Other two are macroscopic and microscopic. These two are when we consider the system as a one single unit. property which can be defined considering the system as a one single unit are called macroscopic properties. Then microscopic properties are properties which we can define for one single particle. For one single individual particle is microscopic properties. Then if we use any of these qualities to explain a system, that is called state of the system. Whatever the property we are using, if we explain to about the system, that is called state of the system. As an example, you know two different states, standard state and also room condition. Room condition. Standard conditions are temperature is 0 degrees Celsius, pressure is 1 atm, room state or room condition, same pressure, but temperature becomes 25 degrees Celsius. Okay. So initially, before starting the experiment, first part is called this, here we are explaining that. So that is called this starting state. Starting state means just the initial condition. Then final state is the final condition. Once all these reactions occur, whatever these interactions done, then the second state called the final state. A system can interact with its surroundings by means of exchange of matter, heat, energy, or maybe all. Okay, then state function. State is again these properties, extensive, intensive, macroscopic, microscopic. Function means it is changing with these properties. And here in energetics, state function is something that depends only on initial and final, but does not depend or independent of how the conversion is going on. As an example, if A goes to B, it doesn't matter whatever the path it is using. So these state functions are the properties which are not changing. As an example, regardless whatever the mechanism, whatever the paths they are using, entropy of the system depends only on this A and B. Enthalpy of the system is also only depends on A and B. Those are called state functions. Then what is this spontaneous reaction, non-spontaneous, reversible reaction, irreversible reaction? Just you can go on easily with the note. Moving on to the next important part, heat change. Why we are talking about the heat change? Because heat change at constant pressure is the enthalpy. So we are going to talk about enthalpy, entropy, and then Gibbs free energy. So heat change at constant pressure is entropy. So heat change is also a form of energy. And we are using these two equations. Both are exactly the same. Q equals mc delta T, lowercase or uppercase. Usually for lowercase using when you are doing this Celsius temperature, uppercase used when you are doing this with Kelvin temperature. Anyway, Q is the heat change. And also M is the mass. Usually go with kilograms, even grams is acceptable. C is specific heat capacity. The unit can be joules per Kelvin per kilogram. That Kelvin can be Celsius. Kilogram can be grams, depending on the situation. This delta T mean the temperature difference, either Celsius or Kelvin. So what is the heat capacity? In heat capacity, it is increasing the temperature by 1 degree Celsius. How much heat is required for that? We are not talking about the quantity. Whatever the quantity, if we increase temperature by 1 degree Celsius, whatever the heat required to raise temperature by 1 degree Celsius, that is the heat capacity. What's the specific heat capacity? If this amount become 1 gram, if the amount become 1 gram, then heat capacity becomes specific heat capacity. So that we can write heat capacity equals mass into specific heat capacity. Okay, just to show you, I'm doing this first question. We're going to calculate this. This is how they are calculating the heat capacity. Okay, we're going to calculate heat change. 25 cubic centimeter of 0.1 m sodium hydroxide. So CV of sodium hydroxide given. 50 cubic centimeter of 0.1 m HCl. CV of HCl given. So mixing, density of the solution is given. Specific heat capacity is also given. Temperature difference given as 5 units. We have everything to find this heat change of the system. To find heat change, this is the equation we are using. Q equals mc delta T. Delta T they were given. That's all right. Delta T equals 5 units. Whatever the given units of specific heat capacity, we are using that unit for temperature. They were given here Kelvin. They were given here Kelvin per Kelvin. So we're going to get that temperature change as 5 Kelvin. Since they were given Kelvin here, I'm going to get this as 5 Kelvin. Okay, so that the temperature difference part has already solved out. So the next part is specific heat capacity. That's given as 4,150 kilojoules joules per Kelvin per mole. That's also then solved out. Then only the next parameter we need is the mass. How do we calculate mass? This assumption they are using for dilute solution, density of dilute solution equals density of water. But if they have given the density, we're going to use that. If they were not given that, we are using the density of water. But here they were given that density. And also, how much is this volume then? Total volume become sodium hydroxide 25 cubic centimeter and HCl 50 cubic centimeter. So that total volume is this 25 plus 50, that is 75 cubic centimeter. 25 from HCl, 25 from sodium hydroxide, 50 from HCl. Density given, density equals mass divided by molar mass. To get mass, that need to substitute here. Mass equals dV, go with dV, 84 grams. But since they were given specific heat capacity in per kilogram, I'm going to multiply this mass by 10 to the power minus 3 to convert this into kilogram. So the only necessary data is those three. So we have the mass, we have the specific heat capacity, and we have this temperature difference. Per Kelvin, Kelvin cancelling off. Kilogram, per kilogram cancelling off. So that only joule is remaining. So that is the energy unit. So that's acceptable. So we can calculate heat change. Question number 2. Whoever these new students who came after we done this, I'm just showing the note to you. Otherwise, if you want a photocopy, you can ask a friend in the class to get a photocopy. I hope that everybody would support for this. I just want to emphasize you something. It's when you're supporting your friends, you are increasing your merits. So you are not only your friends, couple of your friends who are having lower marks can go from your city if you support and go together with your friends. If you're supporting your friends, if you are exceeding these merits, so you are giving extra opportunity to your friends as well. So keep that in your mind. See, I did a couple of questions. Then, when we are doing a chemical reaction, we can do a chemical reaction at constant pressure or at constant volume. Okay, what is the difference? Okay, constant volume. Here we are using this fixed cork, but constant pressure, to this cork, we are fixing this piston. So when the pressure is increasing, piston is going up to decrease pressure. If the pressure decreasing, piston is going up to increase the pressure. So whatever the way, pressure is controlling by the piston. So this is constant pressure condition and this is constant volume condition. Okay. So the example I've taken is the reaction between magnesium and HCl. So this is generating its own heat because this is reaction of active metal and acid. So that generated heat we can measure separately. So you can get heat change or Q. But if the pressure is constant at this situation, if the volume is constant, when the volume is constant, that generated heat also in increasing the pressure, it is cannot increase the pressure. So that this excess pressure, how do you make the pressure? Pressure comes with collisions per unit area. So that pressure is not increasing here. Pressure is increasing here mean collisions are increasing. When collisions are increasing, these collisions also tend to create heat. So that in this system, when pressure is increasing, it is also collide onto this thermometer bulb. So it increases the temperature around the thermometer bulb too, so that not only the heat generated by this reaction, but also the heat generated by these collisions are also occurring. So that in here, at constant volume, when the pressure is increasing, by that increased pressure, it is generating new temperature. So this is giving the constant volume conditions give fake higher energy reading. But here there are no such situation. So that because of that, to measure heat change, we are using constant pressure rather constant volume. Full page is here, you can read if you want. See, this is the explanation. You can read this pausing the page. Okay. So that I already told you guys, enthalpy is the heat change at constant pressure. So that we can write delta H is heat change at constant pressure. Enthalpy change is the heat change at constant pressure which occurs during a chemical reaction. Okay. So change we are getting always with the difference of something. Here the difference of product enthalpy and reactant enthalpy. So enthalpy change equals so that product enthalpy minus reactant enthalpy. So unit of enthalpy is also kilojoules per mole. Okay, enthalpy change is directly proportional to the amount of substance in the system. So when we are defining enthalpy, we are always defining to per mole, because if the number of moles is changing, enthalpy value is also changing. So thermodynamically, heat change or the enthalpy change can be classified into two parts, exothermic and endothermic. Exothermic and endothermic.